Working with polynomial functions, as we've talked about over the past week or so now, right? As we look at polynomial functions, make sure you understand that we're looking at graphs that have nice smooth turns to them, right? Their domain is all real numbers. So as I go from left to right, I'm going to have ordered pairs at every single x value, okay? There's some things that we key in on as we deal with these. And that's what we want to focus on today, is making sure we're highlighting what are some important aspects that we need to take away as we work with polynomials. All right, these first two is definitely something that we need to be able to do as we begin to work with any polynomials, identify these things, all right? So as we talk about that, one thing that we definitely need to look at here is what is the degree of a polynomial, right? What does the degree of a polynomial represent? What term do we normally look for? A variable with an exponent, but that exponent is going to be what? The highest exponent, right? We're looking for this idea that we're dealing with what is the greatest exponent that this expression will have. Are these terms, though? What does it mean when we see parentheses or something right in front of parentheses? What operations imply? Multiplication. So these are not terms, right? This is a factored form. So make sure that as you work with this, that we're recognizing right away that this is in factored form. Because of that, we have to be careful with how we interpret this. Specifically, instead of saying, oh, I see x, that squared there, that's my degrees, we need to recognize the number of factors represents the degree, right? So how many factors do we have here in the first one? And how many factors do we have the second one? There's only one, right? So then our degree is the sum of that. 2 plus 1 is 3. Got to count the number of factors. Now be careful, always watch your factors too. What's inside each of those factors? It's just x, right? That's an important part to that. It's just x by itself. We need to make sure to watch out for that because those could have exponents on them sometimes, not all the time, but you always want to watch for that, okay? With that said, though, the next thing is to talk about the leading coefficient. Well, once again, make sure you see as I highlighted, it's just x on the inside. So what number is our leading coefficient then? And the number out in front, right? Now, always make sure you check your x values, though, because that is an important part. That's just x. That's why we're able to say -3/5 is our leading coefficient, okay? What's something important to take from that? All right, so because it's negative, we will have a reflection. All right, how about the maximum number? Yep. Us counting our factors, we had 2 factors and 1 factor, so that 2 and 1 summed together gives us the total degree. All right, what's the maximum number of terms that we can have? Where do we get that from? Right, so we take our degrees, we subtract 1, and that's where we get the terms from, right? So make sure you see here, I pulled this from the degree of our polynomial. All right. With that in place, now we could actually go start kind of describing everything, right? End behavior is definitely a place where we want to start. We're just going to do a quick discussion on that. We're going to say, hey, what's the end behavior of this graph? And in that quick discussion, we could do a little quick t-chart. On one side, we'll say x approaches negative infinity, and the other side, x approaches positive infinity. What's another way to state those? Now, that's what we're going to talk about next, but just to make sure we understand what these means, what's another way to state this? If I say x is going to negative infinity, which direction are we going? left. So we could just be like the left hand side of our graph, and that means this other one is the right hand side of our graph. Okay. With that said, then, what is this graph going to do on those two sides? All right. We have four choices. Make sure you see that. We could have something that looks like this, something that looks like this, like this, like this. And we got to determine of those four choices which one we're using. Okay. So with that said, what does this graph do? Why are we saying false? So what's the degree? 3, right? So are both sides the same or are both sides different? Right? So make sure you see here that we're looking at this and saying if one side rises, the other side falls, or vice versa, right? What do we use to help us remember is the key, right? Well, x cubed is going to look something like this. But what did we say is going on that changes that? The reflection, which means now my graph is going to do this, right? So this is going up, this is going down, and we need to match that over here by saying, hey, this goes to infinity, this goes negative infinity. Positive infinity, though, as we've mentioned, is going to be rise, and negative infinity is going to be falls. Make sure you see here, though, the main thing that we take from this is that it's odd. And that's what we use here, that, hey, it's going to be similar to x cubed, right? The difference is we got a little bit more going on, so it's going to take more of an S shape as we go talk about a graph. Okay, so that's going to be what changes there, is that you get more of the curve here because you're going to have two turning points somewhere in that graph. Okay. Questions with those? No questions? All right, so hopefully what you see there, then this is all just kind of looking at it and then interpreting what we see. The next step then is to jump into our intercepts, right? What's the first intercept we can find? My y-intercept, right? We would say, hey, f of 0 equals, and then we got to go plug that in, right? All right, and when you do that, make sure you get 4 fifths. Excuse me. The nice thing there is the negatives go together, and the negative 3 fifths and negative 1/3. On top of that, make sure you see here, these 3's go together. Other than that, it's just 2 squared over 5. Okay, so once you scratch out these 3's and you scratch out the negatives, you get 2 squared over 5, which is 4 fifths. Now, the nice thing about the factored form then is when we go to that next step and say, hey, what are the zeros of our function, right? What is going to be our x-intercepts? Well, that's going to be negative 2 and 1/3. It's already in a factored form, right? So all we have to do is change the sign from what we see to get to that. Okay. That's one of the nice things about having the factored form right away. Just make sure you remember, though, that you take note to yourself that, hey, there is a multiplicity taking place here where the negative 2 occurs 2 times, and the 1/3 only occurred 1 time, as we stated from the beginning. Okay. Questions? Are we good with where these values are coming from? Are we good with where I'm getting this from for the y-intercept? All right, so let's look at the next one. What's different about this? Huh? right? So it's in that general form right now. It's not factored, right? This is a general form, right? We have terms involved. What's the term that I need to focus on, or the terms? Huh? The leading coefficient and the constant. And since it's in order already, right? That's going to be the first and last terms. That's the nice things there. All right. So with that said, if we go down our list, what's the degree of this polynomial? All right. The leading coefficient is what? What's the maximum number of turns? All right. What can I go get now? In behavior, right? Hopefully you see here, I did a degree 3 for both of these, right? So as we go deal with in behavior, the one part that doesn't change is we want to look at it from the perspective of the left hand and the right hand of what we're dealing with. Well, what's going on with this one? What's it going to do on both sides? Are they the same or are they different? So with a degree that is odd, our side, the edge is going to be, the two ends of the graph that is going to be the same or different in their behavior. They're going to be different, right? One's going to rise, one's going to fall. Do we have a reflection? No, right? So we can go straight to this graph here. Remember, that is x cubed from a parent function standpoint. So make sure you see there that, hey, this side's going to fall and the right side is going to rise. Remember, negative infinity corresponds with fall, positive infinity corresponds with rise. Excuse me. You have to make sure to go back to that parent function though. And remember, any odd polynomial, we can correlate back to x cubed. It's not going to be the same because the number of turns, right? If I give you something x to the 7th, hey, I can have up to 6 turns now. So it's not going to be exactly like a cubic, but I can use that to kind of set the overall pattern to expect on the ends of my graph. That's why we call it in behavior. Make sure again that you see here, as I said here, we just call it left hand and right hand. This is the proper notation though, that we would use there. Rise and fall in the same way. Any questions with that? All right, what should I go do now? All right, so what's the first intercept? All right, what is negative 27? All right, so g of 0 equals negative 27, right? That's a nice thing about the general form, right? Y-intercept right away. Whereas over here, we had to deal with those fractions to get to what we were working with, right? So there's a nice change there. But the other side of that then is when I go to find these x-intercepts, right? I'm trying to find the zeros of this function. I got to do some work. What's nice about this statement, though? I can factor it by grouping, right? So I'll have x squared times x minus 3 plus 9 times x minus 3. And factoring by grouping does indeed work. So we get x equals to 3, x squared equals negative 9. What's the issue with that negative 9, though? I have to do the square root, right, because the x squared, but what's the square root of negative 9? That 3i, though, is a big deal, right? Now, with that said, we were trying to find intercepts, right? So hopefully you see here, this is the intercept that we needed. All right. These are not real. You know, that's my daughter's call. Give me a second. All right, sorry about that. All right, so why did I write not real here on this one? Let's jump back in. Because the I. Now be careful here to see that that's not a difference of squares. We could not factor it. Right? So sometimes it's probably safer just to go ahead and do set it equal to 0, right? Make sure again you see that it went from +9 to -9 because I moved it to the other side. When we do the square root though, as mentioned, when we set it up, we have to have plus or minus the 3i. Can't just be 3i, it has to be the two solutions there that we're recognizing with the square property. With that said though, why did I only write one of them up here? Not real. And I asked for what? Intercepts. Now, if I say find the zeros of the function, right? 1, 2, 3. You have all three. Okay. So keep that in mind. Any questions here before we move forward? All right. Anytime you get solutions that have complex values, though, know that you're always going to get that plus or minus situation. All right. Specifically, what you're going to see here, these are complex conjugates. I know we've kind of talked about this before, but I want to hear the, oh my goodness. I might be taking the afternoon off, y'all. Complex conjugates, okay? Make sure you see here, they're both the same value except for what? The negative, right? +3, -3. -5, +5. Make sure you see it's the complex term that's negative or positive, right? That's what changed. Like on this second one here, it's 2 and they're both +2. What you're going to find here, though, I make sure to put this up here because when we're solving polynomials, if you ever get a complex solution, it has to have its complex pair. And what do I mean by that? The conjugate of that. If you do not have both of these, you made an error. Well, let's look at this. When you do 3i times -3i, you negative. I'm almost done if this wasn't doing this. You get -9i squared, right? What do we have to remember about I squared though? I squared equals what? -1. So that's the part that we have to remember there. Something is going on in this room right now, y'all. So this is -9 times -1, so you get +9, which is what we had there to be. Remember, x squared plus 9. So make sure you see that's coming through. What in the world is going on? I did. What are you bringing in here then? All right. So how do we multiply the next one though?
Are we supposed to like
Right. We've got to distribute out using FOIL method, right? So get 4 plus 10i minus 10i minus 25i squared. Right. Make sure you see here though that when we go through with that, we're left with this statement here. That's an important part to that because as you see here, what just went away? The tens, right? That's kind of one of those aspects of don't forget when we talk about complex conjugates, it's a difference of squares. Now the difference here is because we have that I squared, this becomes a little bit further as far as work is concerned. So there is a little bit more we can do here. Now you're not always going to be asked to simplify these, but my focus here is the highlighting of this term here. That's one of the things that kind of says that I definitely have conjugates. Make sure you see here, a complex number times its conjugate gives us a real value. So everyone see that? The I is gone. That's another thing that's important there, okay? When we use conjugates, usually we're trying to deal with something like that. Let's deal with that. Now, for our perspective, what did I say is important to remember? If you get this as your solution, you need to remember that this also should have been there. That means you forgot to put your plus or minus symbol. The same thing with this. If you get this as a solution, you forgot to put the other one. Okay. Complex solutions always come in their pairs as complex conjugates. Okay. And again, look at three, plus or minus three I's we just found. Okay. Any questions with that as far as conjugates and what that means? All right. And hopefully what you see here, what I'm showing you is a complex number, right? When you multiply with this conjugate, you get rid of the complex part and get a real value. Okay. With that said, I'm going to go through this one a little bit quicker because we've talked about it a couple times now. But if I go through and do this, make sure you have any issues. What in the world is going on? All right, so if I put that down first, are there any issues? So everyone's good with where the 4 and the 3s are coming from? Are we good that I put the same thing for both of these? Right, it's the same thing this time because we have an even degree, right? There was no reflection, right? So both edges are going to be going up. So that's what we're seeing. They're both rising, right? So keep that in mind as you go over here. If you need to, write that out that, hey, this is rise, and make sure you confirm back, hey, they're supposed to be the same because I'm working with a degree 4 polynomial. It's even. It's not a quadratic, but we know the edges will have similar aspects is what we're focusing on there, okay? What am I giving us here again? My y-intercept, right? So make sure again that we're keying into some of that. The next thing though is to go in and find the x-intercepts or the zeros of the function, right? Now, one way that I'll deal with this is that we're going to have to find that x value and the multiplicity of that x value. But the problem here is how many terms do we have? We have 5 terms, right? So we're not going to be able to factor a quadratic. We're not going to be able to factor by grouping. And there's no GCF, right? So we need to go into that idea that we talked about in class last week of, hey, this is a guess and check process. We need to use synthetic division to quickly check as many values as we can. Now, do we want to check just any random number we think of? No. Do we want to use stuff like the square root of 2? No, right? Because that would make it even more difficult. We had to check any possibility. What we use here is is PRZ. What did the PRZ stand for? Right, possible rational zeros. The key behind that is they're possible, right? There's no guarantee they're going to work. Is that clear to everyone? When we say possible, that doesn't mean any of these are going to work. These are just the possible ones. Rational means we want to use integer values or fractions. That's it. If it cannot be written as a whole number or a fraction, we don't want to use it. Is that clear to everyone? And the zeros there is just a reminder that our whole focus with this is to find the x-intercepts, right? And x-intercepts come from the zeros of the function. With that said, what are the 2 numbers that we highlight again? The constant and the leading coefficient, right? Now, remember, when we get here, we always want to do constant over the leading coefficient, okay? Which means we're going to do plus or minus 1 plus or minus 3, because those are factors of 3, right? Make sure you keep that in mind. 1 and 3 are the only thing that I can use from a whole number perspective. The next thing is to put those over 3. But keep in mind, what is 3 over 3 equal? 1. So the only other thing we can use here is 1/3. Okay. The one thing I will say here is these came from my constant term. Everyone follow that? This came from my leading coefficient. So make sure you have in your notes highlighted somewhere a reminder that, hey, when I build these fractions, the constant term goes up top. If you ever get stuck, do this. Doesn't that follow a similar pattern to what I'm trying to do right now? A function equal to 0. A linear is special because it's a straight line, but technically that's similar, right? I have a leading term and a constant term. Solve it. Well, hey, look at that. We add the 5 to both sides and divide by 2. Where did the 5 end up? What? The 5 is up, but make sure you see that because the 5 is our constant term, right? So everyone see how the 5 is our constant term? And just making up this random equation, we're able to remind ourselves, oh, hey, the constant term goes up in the numerator, right? The leading coefficient goes in the denominator. Okay, so keep that in mind. What do you like about this list, though? How many possible things can we use? Right, plus or minus, there's 6, right? 3 numbers with opposite signs. Where does someone want to start? If it works right away, again.
I know that's gonna work.
No, it's the chord. All right, so remember what we're doing here is the synthetic division, right? 3 was picked first. I would have started with 1. That's just because I'm a very habitual person, so I start with what I know to do. Okay, is there anything wrong with picking the random number here? Absolutely not. Okay. If the constant term was 27, should you use 27 first? Probably not. Okay. But again, there's nothing that says it won't work. It is a possible 0, so keep that in mind. Go back to the one I did Friday and Thursday. We never picked the biggest number, right? But that doesn't mean it can't work. 1/3. Could you start with 1/3? Absolutely. I don't think it's going to be that bad to work with 1/3. The only problem is what's 4 plus 1? So if you get that 5, you're going to have 5/3 or possibly moving forward, right? Not that that's guaranteed to happen, but just know that you'll have to deal with fractions. Okay. With that said, what happens? By randomly picking 3, what did we get that we wanted to see? We got the zeros. That cleared everyone? That means then that h of 3 equals that remainder. Make sure you remember by the remainder theorem that h of k equals whatever the remainder is. Okay, that's definitely an important part. Now, for our perspective here, though, the key that we're taking from this is that this is true. X minus 3 is one of those factors we're looking for. Okay. Now, with that in place, though, I need to move forward and find more of them. So what do I need to write down next? The quotient, right? Make sure we get the quotient, right? That, hey, this is 3x cubed plus 5x squared plus x minus 1. Now, make sure you remember also moving forward, we're going to use that quotient to make the work even more fast, more straightforward and quicker. One less thing to deal with. Okay. What changed, though, is we went from h of x down to the quotient that we need to make sure to take note of. There's 4 terms, right? Can't factor by grouping work, though. 3 dub 5 don't work together, right? You should still try, though, right? Make sure you remember the one I did Friday, I believe the factoring by grouping did work, okay? But it won't work here because 3 and 5 will not give us 1 and 1. All right. But make sure you see here what happened here. Why am I circling this particular term? That's our constant term, right? What was our constant term to begin with? So when I got down here, it's 1 now. So should I use 3 or -3 moving forward? No, right? We should only use 1 or -1 or 1 or 1/3 or -1/3, right? Do not use 3 anymore. Does everyone see that? With that said, let's try -1. I'm going to pick this time. Hopefully it works. If it does, it's going to work. I was about to say it better work for me to pick it. That'd be messed up. Now make sure you see here, I'm putting in blue to make sure to highlight I use the quotient instead of the original function. Okay, all we care about right now is a remainder of what? Yeah, anything else is useless. All we want is a remainder of 0. And look at that. Works out. Okay. With that though, we now know that h of -1 equals 0. But h of x can be written as now x minus 3 times x plus 1. Make sure you see here again, it's a plus 1. We have to change the sign for the factor. And then our new quotient is what? 3x squared plus 2x minus 1. That's actually kind of nice, by the way. Any questions, though, with the 2 synthetic divisions we did here? So everyone's okay with those 2 steps that we knocked out? Are we done, though? We still got an x squared, right? Now, the nice thing about this is make sure you kind of keep track. This is x equal to 3, x equal to -1. But we can go try to factor this now. If you chose to use the quadratic form, if you chose to do synthetic division with this, is it wrong to do that? Not at all, right? But understand with the quadratic formula might be needed, which is why I accidentally said it, because this is not always going to factor. The nice thing here is this one should, if I remember right. We get -3 and +2, and look at that. -1 times 3 and -1 plus 3, and we're good to go. Now, what I want to do, though, is rewrite this problem. So we go with where I'm getting these factors from. Use your factoring by grouping, of course, here. If you need to see where I got them from, that's where you fill in as you need. So if you need to go do factoring by grouping here, go write out the steps to do that. Be careful here, though. I didn't put -1 and +3 here. That's not how we factor that, right? Because it's 3x squared. So I made sure to put the 3 with x itself. So you have to be careful. So if you're going to make that mistake, then I encourage you to go back and use factoring by grouping as we've done in the past. Okay. With that said, though, as we deal with this, we now have, was it x minus 3, x plus 1 squared, and 3x minus 1. Make sure you see here that I chose to use -1 for synthetic division, so we got 1 there, right? That's where the first one's coming from, is this synthetic division. The x plus 1, that second one came from me looking at this separately. All right, and that came from my quotient on that last synthetic division. Does everyone follow why I put x plus 1 squared? All right, so that gives us +3, -1, and +1/3 for our zeros. Make sure you see here, though, we should have 4 zeros, not 3. What do I need to make sure to take account of, right? That's where that exponent on our factors comes into play. We have to make sure to remember that. I have 1 factor for the x minus 3. I have 2 factors for the x plus 1. And I have 1 factor for the 1/3. What do those values add up to? Why is it that it's important it adds up to 4 again, though? That's my degrees. Does everyone follow that, though? Because that is definitely something important that we need to make sure to see that connection back to the beginning. Any questions or concerns there? All right, so why am I putting these points on my graph first? What do these 4 points represent that I'm putting here? What 4 points did we just go find? Intercepts, right? My y-intercept and x-intercept. So make sure you see here that as I listed that table out, I made sure to plot those points too, the same way that we saw them. And don't forget h of 3 was one of the first things h of 0 equal to 3, sorry, was one of the first things we highlighted. Why do I do this then? Where's this coming from? That's my end behavior, right? Both sides are going up. From here, I got to figure out how to draw the middle, right? This is where multiplicity helps us. How many factors of -1 did we get? So how many x plus 1s did we have? The x plus 1. We had 2 of those, right? So remember, that means I'm going to go down and I'm going to bounce off of that, right? Well, that means I got to go up here and cross that y-intercept. But why did I turn back down? Because I have 2 more intercepts to get through, right? So I got to turn back down and go up through there. Okay. Now, is that a perfect graph? No, things I'm going to look at. Did we have this to where it goes through and bounces off of it, almost kind of like a quadratic when we zoom in? Did we cross straight through these to where it's almost linear-like? Those are key things to watch for. This is definitely a point that we need to make sure to use, right? Y-intercept we can get from the constant term. Now, what's going to happen is, for all we know, this thing dips all the way down here. Right? But what did I say we're going to need to go talk about that? Okay, well, what is this? I'm going to use these as capital H's. What was that thing called? We saw it like this. We do need to remember this. Am I going to ask you to do this with this function? Absolutely not. That'd be unreasonable. Okay. But the difference quotient is the average rate of change, right? So if I go in here, what's the average rate of change between these 2 points as I go from left to right? You have to go up or go down? Down. So it's a negative value, right? As I pick these 2 points over here and I do that, it becomes a positive. So we have a negative and positive. Well, if you go from a negative value to a positive value, what must be in between them somewhere? If you're going from negative numbers to positive numbers, what must be between them somewhere? 0, right? Well, isn't that what the slope of a horizontal line is? Now, the problem is, can I just plug in 0 here? Right? H can't be 0 here, right? So that's where we go in and like understand that at this point, we could have done this on that function. That would not have been fun, but still we wouldn't be able to do anything because H can't be 0. Does everyone follow that? But that's where we focus on that. That's where the difference quotient would come in and help us, okay? What you'll find is if any of you took calculus, just for the fun of it, of course, you would see that's where the difference quotient to help explain that, okay? There's other things we have to use as well. Questions I can further clear up with how I got my graph though. All right. I apologize about the technology issues we face, but that is it for today. I hopefully you're catching on. I've done the same thing for 3 days now. So we've had plenty of time for discussion and questions. If you're not doing the work though, I can't help you on that because I've been very clear about how practice is what's really needed. If you need more than the homework assignments, open up that e-text I gave you from OpenSex. I got assignments in there as well. Have a good day though.